Good morning, afternoon, evening. This is Mr. Precella. Today we're going to work with some exponential functions in Math 1324. This is a math for business majors. And exponential functions have a variable in the exponent. So here are a few functions. It asks, okay, classify this as linear, quadratic, exponential. A linear function has no exponents. A quadratic function has an x squared. An exponential function has the variable in the exponent. So this first function, the x, is up in the exponent, so this is exponential. And then of all the numbers in the world, my math lab decided to regenerate this problem with the exact same. It's another exponential. Here, this one. Oh wow, there is an x squared. This is sort of tricky. But where is the x? If there's an x in the exponent, then it's exponential. So even though this one has an x squared in it, it's still exponential. There's an x in the exponent. To graph an exponential function, I suggest just plotting some points. For instance, let's put from 2 to negative 2 down. If I plug a 2 in for x, 6 squared is not 12, it's 36. 6 times 6. 6 to the first power is 6. Now 6 to the 0, here's a common mistake. Here's a rule from algebra that you've seen somewhere. Any number raised to the 0 power is 1. So when you put a 0 in here for x, you'd have 6 to the 0 power, which is 1. Sometimes students don't believe this till they see it on a calculator. If we take 6, on this calculator to enter an exponent, there's this little caret key raised to the 0 power. Let's see, the glare's sort of bad. 6 to the 0 is 1. There's nothing special about 6. 7 to the 0 is 1. 8 to the 0 is 1, and so forth, okay? So that's why I wrote anything to the 0 power is 1. Now what about plugging a negative 1 in? 6 to the negative 1 is not negative 6. Here's another rule from algebra. Something to a negative power, a negative exponent doesn't mean a negative number. It means 1 over. So 6 to the negative 1 means 1 over 6 to the positive 1. This one, you'll see the pattern better maybe. 6 to the negative 2 doesn't mean negative 36. A negative exponent means 1 over 6 squared 36. Now you're just going to choose which graph, and these are sort of small here, but when you're actually doing it on my math lab, there'll be a little magnifying glass that you can click and it'll blow it up. I'm going to actually sketch out the graph like this. Okay. These numbers are so large, like right 2, if I'm letting each one of these little marks be 1, right 2 up 36 would be off the page. Write 1 up 6. 1, 2, 3, 4, 5, 6. Over 0 up 1. Then, okay, look at this. Left 1 up 1/6. Can you imagine? Ooh, let me bring this up a little. Can you imagine moving up just 1/6? That's going to be pretty close to that x-axis. But nothing like left 2 up 1 over 36. Can you imagine breaking this region up into 36? It's going to look a lot like 0. When we connect these, the graph, imagine right 2 up 36. It's going to keep going up real fast. And here it's just going to look flat. This is the typical shape of an exponential curve. One end going straight up and the other end flattening out. So, and these graphs are very small here when I printed them out, but on my math lab you can blow them up and magnify them. So, but hopefully you can tell it. The graph looks like D. It's graphing an exponential curve. Let's see. Here, number 7. You're going to be using your calculator and that exponent key I was trying to show you. To punch in an exponent other than squared. Like here's an x squared key. Right there. This is the key right here that you'll use for something other than, oh yeah, right there. You see it? Little carrot top. Number 7. If $1 is deposited into an account paying 21% compounded annually, then after 1 year, after 2 years, the account will contain this much, 1.21 to the T dollars. Use a calculator to complete the table. Well, they're plugging numbers in for T. 1, 2. To get this number, let's plug a 3 in for T. So you're trying to figure out 1.21 to the third. And to do that, I will punch in. Let me see. If I remove this, does it show better? Maybe it doesn't make a bit of a difference. I'm going to punch in 1.21. Oh, I think I hit 2. Let's see if I can tell what those numbers are. Well, that'll help. The light switch goes off. I don't know what's going on with this, but it's always 1.21. Hit the little caret here to the third. Okay, how are we told to round this? We're told to round it to 2 decimal places, and the number that I have is 1.7715. 2 decimal places, it would just be 1.77. And then to fill in this one, 1.21, in place of the T, you put a 4. 1.21 raised to the 4th. 2.143. 2.14. Then it says, okay, graph that function. Let me find some blank paper. You know what? Maybe I don't need blank paper. Maybe just looking at these points here is enough to figure out what the graph looks like. Okay. It should have if at t equal 1. Well, first of all, it doesn't show 0, but if you know your rules about a 0 exponent, 1.21 to the 0 power, 1.21 to the 0 power would just be a 1. So which of these looks like it's passing through 1? Well, first, there. It's not this one or this one. And again, these graphs are so small, you'll be able to magnify them. So it's either this one here or here. So look at how these are set up. If we get up, okay, so right 1 at 1.21, right 2 at 1.46. Let's see, like 1, 2, 3. Look right here at 3. It should be just at 1.77, but on this one it looks like at 3 it's up to 5. Right 3 at 1.77. Well, I guess that's about, it's going to be B. If you want to plot these points, or some of you may have know how to punch graphs into a graphing calculator. If you know how to, then great. It's not enough, we don't do this enough for us to worry about having to do that in this class, okay? Here, the main thing you're supposed to do here is just plot some points. And they're sort of telling you these points. So which one of these passes through these points, and especially if t is 0, y would be 1. That's what lets us knock out these A and D. And then maybe looking at right 3 at 1.77, it's certainly not C. So it is B. C. What about number 8? The number of cell phone accounts in a certain country has increased exponentially for the last decade. Estimate the number of cell phone accounts in 2004. So we're given this function. We're told that x will be, this function is good for values, x values between 0 and 9. That's what that's saying. X equals 0 corresponds to 2000. So we want to find the number of cell phones in 2004. If x equals 0 were 2000, then x equal 1 would be 2001, and so forth. For 2004, would you agree that x is 4? In words, x is the number of years since 2000. So x is 4. Let's just plug a 4 in right here. Here's what I'm going to have to punch into my calculator. 113.6 e to the 0.125 times 4. So I'm going to try to do this. It's going to be hard. There's too much glare on here. Ooh. Okay, I punch in 113.6. Now to hit this E key, that E is it's an irrational number, 2.718281828 approximately. On your calculator, that E shares the key, or at least on mine, it shares it with ln, and it's sort of hard to see it. It's in yellow. Let me see if I get it any brighter. Can y'all see that there is a, on here with the ln, there should be a yellow E key, and the lighting is just so bad here, I can't tell if y'all can see that or not, but it's sharing with the ln on my calculator. It should look, the key be labeled e to the x. To get to that yellow e to the x key, I have to punch in second e to the x, and then I punch in 0.125 times 4. I'll close the parentheses. 187.2947. How do they want us to round? Okay. let's see, round to the nearest thousand as needed. Well, let's see, 2947364. That's the number that's showing in the calculator. Now, does it make sense to say that in 2004 there were 187 cell phones in that country? Well, no. Right here it says in millions, so that means there's this many million. So, since this one doesn't say millions after it here, what I'm going to do is take this number and just say times 1 million. So here's the actual number. It's 187 million. It's 187,294,736.4. Now you're not going to punch in all of that because it says round to the nearest thousandth. Thousand, not thousandth. So let's think of our place value. Since it says thousand, with place value, the first digit right here to the left of that decimal point. Ones, tens, hundreds, thousands. So this 4, we're either going to leave it as a 4 or round it to a 5. And we're going to round it to a 5 because that digit there. 187,295,000. Okay, do y'all see how I rounded that? 1. When you plug 4 in for x, you're going to get this 187 point decimal number. That's millions. So multiply by a million and then round how it tells you. Round to the nearest thousand. It's a little tricky there, that rounding. Let's see, number 9. Let's see, what's this one? It's another one where you have to plug in some number. The scrap value of a machine at the end of its useful life is given by this formula where C is the original cost, N is the useful life, and R is the constant annual percentage of value lost. Find the scrap value of the following machine. Well, we're plugging in. The original cost is C, that's 45,000. The life, that's N, the life of the machine, and R is the annual rate of loss. You're not going to write 9, you're going to write, how do we write 9% without that percent symbol? Well, to write it as just a decimal, you move the decimal point 2 places to the left, so 0.09. So here's what we need to punch in. 45,000, parentheses, 1 minus R to the n power. I'll get my calculator again. Hopefully you have a calculator similar to this one, but this is the one I'll be using for demonstration, showing you how to punch in. Now, if you have trouble punching in, the Math Learning Center is a good place to go to get someone to help you punch in the stuff in the calculator. 45,000, parentheses, 1 minus 0.09, close parentheses, raised to the 4th power. Enter. 30858.73. Let's say it's told to round it to dollar and cents. So let me see how much it wants us to round it to. Let's see, just round to the nearest cent. So after 9, or no, after, let's see, what are we told to find? The scrap value. The scrap value of this machine is 30,000. Let me see. Oh wait, once again I messed up on something. This has not been my day. N is 9. Where did I get a 4? Oh, I guess I didn't want the 2 9s. Okay, so this N is 9. I'm not sure where I saw a 4. Maybe I'm just rushing too much. So I need to correct what I had written there. I was thinking that was a mighty high scrap value. Okay, you see I punched in a 4 for the exponent and it should have been a 9. I'm not sure where I got a 4. 45,000 parentheses 1 minus 0.09 close parentheses raised to the 9th. Okay, that's a better scrap value. $19,256.84. I guess it's the fact these lights just keep going off in this room that's annoying me or distracting me. It's never gone off so much, so quickly. So there's the scrap value. $19,256.84. And the rest of the problems in this assignment are plugging numbers into the calculator. You have little functions. Let's do this one here. Number 12. I'll just do these until I run out of time. The total revenues of consumer electronics since the year 2000 are approximated by this function. And this is where t equals 3 corresponds to 2003. So if t equal 3 is 2003, we'd use t equal 4 for 2004. For 2009, t would be 9. And for 2012, t would be 12. So it's a matter of me punching this into my calculator. Okay. So I'm sorry if there's a bad glare. I'm going to plug a 4 in for t. So to do that, let me see. Okay. If I do it like this, I'd punch in 79.1. And then times 1.1 raised to the 4th power 115.81031. We're told to round to 2 decimal places. Oh look, I like this, the way they just say billion there. You don't have to then multiply by a billion and write out the big number. So rounding to 2 decimal places would be 115.81. Now do the same thing, plug a 9 in, 79.1 times 1.1 raised to the 9th, 186.51. How y'all would round it to 2 decimal places? Oops. Okay. And then for the year 2012, plug 12 in. So plugging a 12 in, let's see what we would get. 79.1 times 1.1 raised to the 12th, 248.249. Would y'all round that just to 0.25? Let's do number 13, just because it has one of those with the E in it that you need to find the E on your calculator to plug in. So it's been found that a worker new to the operation of a certain task on the assembly line will produce P of T items on day T. So T is the number of days they've been working on that assembly line. For instance, if they've worked no days, if T was 0, E to the 0 is going to be as 1. 25 times 1 is 25. So if they haven't worked on it at all, you wouldn't expect them to be able to produce any items on the assembly line. How many items will the person produce on the first day? Well, T would be 1 here. So let's see if I can show you. I'm plugging a 1 in right here for this T. Y'all see that function? It's 25 minus 25e to the negative 0.4t. That's the function written larger. Now I'm about to plug a 1 in for t. Turning this on. Okay. 25 minus 25. My E key is in yellow on this LN key right there. I'm not sure if it shows at all. And so to get that, I go second E to the X. And now I'll plug in negative 0.4 times 1. Notice to enter a negative number, you hit this one down here. Ooh, you can see that. This key, minus key right here is subtraction. So to enter the first minus, I hit subtraction. To enter this minus, I'm hitting negative. And close the parentheses, enter. So we get 8.24199 ... So on the first day, if we round this to a whole number, the worker's able to produce 8 items. Now he should get fast as he progresses. The longer he works there, the faster he's going to be getting. The next question is, what's the maximum number of items the worker will be able to produce? Well, there's got to be some sort of limit, okay? There's no way we could say, well, he's going to ultimately be able to produce 1 million, 1 billion, 1 trillion. It's just going to keep going and going. There'll be a point at which he gets as good as his job as he can get, and he can't keep producing more and more just because the assembly line can't move that fast. Maybe the easiest way to answer this is, let's suppose he's been on the job for 1,000 days. You agree after 1,000 days, that's probably about as good as he's going to get. If we plugged a 1,000 in for T, let's see what he's doing there. Okay? If I plug a 1,000 in for T, start off. 25, I'm hitting minus for subtraction. 25, now I hit second. LN gets me that E to the X key that you might not be able to see. Ooh, there. Negative 0.4 times 1,000. Close parentheses. Look at that, 25. You see, here's the slowness factor. If he's new, this is how much it's been. It's slowing him down. The maximum number he can produce is just 25. The assembly line won't go any faster. Okay? A skilled employee, the most they can do is 25 a day. Okay? But right when they're brand new on day 1, 8 is all they're able to do. Let me see. Yeah, the rest of this assignment is just, here's some functions. You just got to sort of practice plugging in to your calculator. One more. I'm trying to decide if we have time to do one more or not. How about number 11? Just real quickly. The amount in megawatts of energy generated in a country from wind power can be modeled by this function. Where t equals 0 corresponds to the year 2000. This W naught, that little subscript of 0 is usually read W naught. And that's the initial amount in the year 2000. The amount generated in the year 2000 was that. Whatever amount corresponds to that initial year, that's the W naught value. And you can figure that out because if you plug a 0 in here, the 1.7 to the 0 is just a 1. So you're told that in the year 2000, it should be 2590. So W naught must be 2590. So this W naught, that first number there, is just the initial value for whatever year you're starting with, 2000. Now once you know that, here's your function that you're going to be punching in. W of t equals 2590 times 1.70 to the t. That's the function you plug into now. Okay? So for the year 2008, if t equals 0 is 2000. For this one here, I'll plug an 8 in. And then for 2015, you would plug a 15. Let me see if I can get my calculator to show without too much glare. I'm sorry about this glare. 2590 parentheses 1.70 close parentheses raised to the 8. We're told round to 2 decimal places. So that's going to be 180,672.12. And for 15, I'm just going to replace that 8 with the 15. 2590 parentheses 1.70 raised to the 15th power. Same instructions, round to 2 decimal places. 7,413,675.70. So I think that's enough for this assignment here over exponential functions. The rest of the problem, you're just given some, you got to muddle through reading it, and you're given some sort of function, and you got to plug in. So I'm glad we did number 11 because that one was slightly different. And the rest of them are all just the same type. So work on these exponential functions. If you're in the online class especially, don't allow yourself to get behind. I know it's tempting to, put it off. But eventually, you're going to have some tests and you can't be putting those off. You'll learn this, and this will be a much better experience for you if you just go slowly about it, stay caught up, and don't allow yourself just to get real far behind. So work on this stuff, and I'll be talking about logarithms the next time you hear my voice. Okay? Bye-bye.